Lab 5, Choose Your Own Adventure. For this lab, I chose to film a ball as I threw it up and then watched it come back down. The main things I wanted to observe in my video were the energy principle and Newton's second law. The energy principle states that kinetic energy is equal to 1/2 mv squared, U equals mgh, and delta E is equal to the change in kinetic energy plus the change in gravitational potential energy. If energy is conserved in the system, then delta E will equal 0, which is the case in my video. Newton's second law states that the final velocity is equal to the initial velocity plus F net over m times t, and the final position is equal to the initial position plus velocity times t. I ran the code predicting the motion of the ball using both the energy principle and Newton's second law, and I then compared them and found that they were very similar, which would make sense since they should both predict the same thing. After inputting my video in Tracker, I set the length of the door and then followed the path of the ball. Over here, we can see a position versus time graph of the ball in the y direction. We can see that it is a quadratic shape, which makes sense as the ball slows down as it goes to the top and then speeds up as it goes to the bottom. We are also given a table over to the right of the ball's time and then its x and y position through its trajectory. We can use these to calculate the initial velocity with which the ball was thrown upwards with. We know that final velocity is equal to initial velocity plus acceleration times t. We know that at the top of the trajectory, the ball's velocity is 0, so we can then set this equal to the initial velocity plus gravity, which is the acceleration of the ball, times t, which we can look in Tracker and find to be 0.268. After plugging in these values, we get that the initial velocity of the ball is 2.63 meters per second. For the first code I ran, I used only Newton's second law, so I set F net equal to the vector of the force of gravity acting in the negative y direction, and then I set the velocity of the ball and the position of the ball using Newton's second law. After running this code, we get the motion of the ball on the left, as well as the position versus time graph on the right, which both match those from the Tracker video. Next, we used only the energy principle to calculate the predicted motion of the ball. First, we must set our kinetic energy and our potential energy equal to their respective values, kinetic being 1/2 mv squared and potential being mgh. And we must then initialize the initial kinetic energy as well as the initial potential energy. In this case, gravity is still equal to the negative m times g in the y direction, and so this is equal to F net. We can still use Newton's second law to update the velocity and the position of the ball. We can then find kinetic energy using the new position and the new velocity of the ball, as well as delta kinetic energy by subtracting the initial kinetic energy. We can also find potential energy by using the new position of the ball, as well as the change in potential energy. After running this code, we will also have a plot of the change in kinetic energy, the change in potential energy, as well as the total energy, which will show that energy was conserved in this case since delta K plus delta U is equal to 0. After running this code, we get a model of the position of the ball on the left and an energy graph on the right. The red line represents the kinetic energy, which we can see decreases throughout the entire trajectory of the ball, and the blue line represents the potential energy, which we can see increases. We can also see that the green line, which represents the total energy, is 0, meaning the energy was conserved during the ball's trajectory. In conclusion, energy is conserved in the system, and we can correctly predict the motion of the ball as it is thrown upwards using the energy principle as well as Newton's second law.